Hello everyone, welcome to part 5 of Motion Along a Straight Line. I'm Jaylu from toysandphysics.com, and today we'll start to talk about acceleration. So far we have not touched on this, but here's where things start to get a bit more complex, so make sure you pay close attention. We'll start from the very basics, but eventually this will be a sea of equations that we can use to facilitate the process. However, like I said on part 4 of this series of videos, don't rely on memorizing equations if you don't understand how and when to use them. It is far more important to know how to analyze a situation than just plug numbers into a formula and start making calculations. Now onto our topic. Very simply put, acceleration is defined as a change in velocity over a period of time. Again, acceleration is defined as a change in velocity over a period of time. If something moves at velocity 1 and then it changes to velocity 2, we can say this object accelerates. Just like velocity and displacement, acceleration is a vector quantity, so it has magnitude and direction. Acceleration can be positive or negative. The plus or minus sign may not have a physical meaning like we would expect. Instead, if the sign is the same than velocity, we say both acceleration and velocity go in the same direction, and thus the moving object must be speeding up. On the other hand, if acceleration and velocity have different signs, both vectors go in opposite direction, and that is when we say that an object is slowing down. Notice this doesn't mean that if only both signs are positive, the object speeds up, as it could be that both signs are negative and the object is still speeding up, but in the negative direction of the x-axis. Now, the equation here is for average acceleration, v2 minus v1 over t2 minus t1. This is the acceleration from v1 to v2 over a period of time. And just like the idea of instantaneous velocity, more than often when we talk about acceleration, we refer to instantaneous acceleration. So instantaneous acceleration is dv over dt, where dt means that t is approaching to 0, and thus the value of acceleration is at that instant. From this last equation, we now know that acceleration is the derivative of velocity, and velocity is the derivative of position. Thus, acceleration is the second derivative of the position equation. Let's see a sample problem to better understand this. Here we have a huge marble run set where the position along the x-axis of the marbles is given by this equation. X equals 4 minus 27t plus t at the third. X is in meters and t is in seconds. With this, we are asked to, number 1, find the marbles' velocity and acceleration functions. Number 2, find if there is a time when velocity equals 0. And number 3, describe the marbles' motion for t greater or equal than 0. Again, you can visit the page of Motion Along a Straight Line at toysandphysics.com to see the solution, but you can always follow along and see how we go about this here. First, we need to find the velocity and acceleration functions, and for that, we already established that these are the first and second derivative, respectively, of the function of position. So we just have to find the derivative of the position function, and we'll get the velocity function. Then we take the derivative of the velocity function, and we'll have the acceleration function. I think I already said function too many times. This goes like this. By looking at the position function, first of all, we have a constant. So the derivative of a constant is 0 as per the differential calculus rules. Then we have this minus sign, so we'll put it there as well. After it comes this 27t term. As per the differential calculus rules here, we should take apart the 27 and take the derivative of the t term, which in this case is 1. We put the plus sign where it goes and go to the next term, t at the third. Here the rule says we have to use the power of the term and use it to multiply the result. Also, the power must be n minus 1. Thus, we have 3t squared. Please notice that I'm not explaining the rules of differential calculus, but just applying them. If you find this a bit challenging, I recommend you to take a look at the rules of differential calculus to better understand this. So now we have the velocity equation. V of t equals 3t squared minus 27. For the acceleration, we do the same thing. The derivative of velocity equation is 6t. So there we have the first part of the problem solved. Now, the second part is easy, since we have the equation that describes the velocity of the marble. To know if there's a time when the velocity of the marble is 0, all we have to do is take our velocity equation and make it equal to 0. Then we solve for t, and we should know the answer. So after a little rearrangement, we have that t equals to the square root of 9, that is plus and minus 3. Now, more than often, we have quadratic expressions to define position, velocity, and or acceleration. As you can imagine, t is a term with a power, and thus when we solve for time, we have more than one result. In such cases, like the one we're studying here, we may have positive and or negative values. In either case, something important to remember is that t can never be negative. Time does not move in the negative direction. In fact, time is not a vector, only has a magnitude. Thus, if you have two results, like in our case here, the positive result is the one that has a physical meaning. Although both are correct mathematically speaking, only the positive result has a meaning for us. It may be that in the future you see and learn about negative times, but for the scope of what we're studying here, time should always be positive. Okay, so this solves part 2 of our problem here. The third part is to describe the motion of the marble for t equal or greater than 0. Here we go. To describe the motion of the marble, we need to understand what happens with its position, velocity, and acceleration. If we evaluate the position, velocity, and acceleration expressions at t equals 0, the marble's position is positive 4 meters. Its velocity is minus 27 meters per second, which means it moves in the negative direction of the x-axis. And its acceleration is 0 because just at that moment, its velocity, it's not changing. From 0 to 3 seconds, its position is now on the negative side of the x-axis. Its velocity is still in the negative direction of the x-axis, and as t approaches to 3 seconds, it becomes 0 as per our calculations before. Its acceleration is 0 when t equals 0 seconds. But after that, it grows and it is always positive. Since the velocity and acceleration have different signs between 0 and 3 seconds, the marble must be slowing down. After 3 seconds, position is still negative. Until a bit more than 5 seconds, its position changes from negative to positive. We already know that at 3 seconds, velocity is 0. But after that, velocity becomes positive and starts to increase. This means the marble moves in the positive direction of the x-axis. As for the acceleration, this was always positive, and since velocity and acceleration after 3 seconds now have positive signs, acceleration acts in the same direction than velocity, which means the marble speeds up. Remember that if velocity and acceleration have equal signs, this means velocity increases. It can be either in the positive or negative direction of the x-axis, but the object speeds up. On the other hand, if velocity and acceleration have different signs, this means the object slows down and the motion is in the direction of the velocity. So there you go. That is all for the concept of acceleration. Please let me know if you have comments or questions and visit toysandphysics.com for more information. I invite you to subscribe to the channel so you don't miss any video I upload. Also, if you enjoyed this video and found it useful, please give it a thumbs up to help me support the channel. Until the next one, bye for now.